there's pretty much, I can guarantee a certain number of questions that you'll get on your diploma when we eventually get around to that. So I know that it seems like it's a long ways away, but one of my goals in the grade 12 course is to start helping guide you towards what they might put on there. And so this is a must know question. They're going to test this, I guarantee it. Like, it's just every year there's one of them on there. The concept basically is a calorimeter, where our goal is to try to find a molar enthalpy. And this is one of the big reasons why I do so many labs, because I want to hopefully help you guys be able to envision in your minds what the heck is happening when they give you a scenario like this. Okay. For me, I always like to relate things back to the very first lab we did, where just imagine you have a tin can and underneath it you put some burning stuff and it lights it on fire. Okay. That basically could be a calorimeter. Yesterday in our lab, though, yesterday's lab was even more basic. It basically was just like, a tin cup kind of thing, and inside you have like a second tin cup, and that's all maybe insulated, and all you do is you just pour the stuff inside and you take the thermometer reading and you see how the temperature goes. This one right here works really well if you've got something that's combustible and you don't want it to light on fire. This one right here is a bit more internal, so that there's less of a percent difference. Okay. But either way, hopefully you have a way of envisioning that you've got a container of water that's getting, well, normally it gets heated up. But if you look at the numbers in this one here, it starts at 20.2 and goes down to 17.8. Right off the bat, that should trigger some thoughts. And if it's endothermic, it means that we can eliminate A and B right off the bat. Right? And little tricks like that will definitely help when it comes to answering questions if you're stumped, because it gives you a much better shot of answering this question now, because you know that it's got to be one of these two. Right? Does that make sense so far? So now, we've done math like this before. They're not going to give you any formulas, but if I were to make up a formula, you should know the MC delta T formula, how that works. And usually we can like make this equivalent to Q, but rather than Q, sometimes it's better just to say that it's equivalent to like delta H per mole if we times that by moles. Now, this is kind of a starter formula if you want to work with that. Sometimes we put a little letter down here in the corner. It probably doesn't matter. It was dissolved. Sure, D. I don't think it really matters at this point. And our job is to isolate for this term here. So to do that, we're going to have to divide by N. And so there we go. We need to know a mass, a C value, a change in temperature, and divide by N. Right off the bat, the most common mistakes I find kids make, especially if it's been a while since they've done this, is they see this number 12 right here, and they think, hey, there's a mass. But that's not the number we're going to use for M. Why? Yeah, it needs to be the mass of the water that's absorbing the energy. And here they played that little trick that I think I pointed out a few times. Water is 1 gram per milliliter. So it's 120 milliliters, means it's 120 grams. Water's value 419 joules per gram degree Celsius. By the way, little side note here. The unit here is in joules, not kilojoules. So when we're done, both of these answers here are in kilojoules per mole. We're going to have to divide by 1,000. Temperature change. What is that? 3.4? 2.4? Brain is not working yet. 2.4. I didn't even type it right into my calculator anyways. Okay, last slide here. We have to divide by moles. In the lab that we did yesterday, in order to get moles, we didn't actually weigh something. We found its concentration. And so don't write this part down here, but we did like a moles per liter times by a liter. Like we had probably 1.01 moles per liter times by 0.025 liters. That's what you should have done yesterday. Today for this example, though, we weren't given that information. We were given grams. So we should use the 12 grams. Oh, come on. And we'll have to divide by the molar mass of this thing right here. Does anybody happen to have that molar mass just to save me some time? That's what this consensus is? 132.17. So long as you put it in your calculator, hopefully you can see that this gram and this gram will cancel, Celsius will cancel, that'll cancel. The units I'm left with is going to be joules per mole. If my memory serves correct, I think it's D. Is that the right answer? Just make sure you divide by 1,000 though to put it into kilojoules, not into joules. How'd you guys do? You get that one right? Awesome. Okay, that's a very standard question. Like, I'd be willing to wager good money. You're gonna get a question like that, maybe multiples like that. So, okay, let's try another one. Take a look at this one and then see whether you can match this one up. I'll try to make it a little bit bigger. It's just a little small here. So here's a numeric response question. For those of you who were in my Math 30 class, they loved starting to put some of these questions on the math diploma, where they give you like a whole list of terms, you know, like 1 through 9 possibly. Here they only went 1 through 6, and then they like to do matching questions with numeric response. I put a lot of these into my grade 11 tests as well. So let's talk about photosynthesis. What is photosynthesis? It's where plants take sunlight, react it with carbon dioxide and water. Okay, so we need carbon dioxide and water. So carbon dioxide is 3. And water is either 4 or 5. Which one is it?
4.
Why 4, not 5? Yeah, I mean, when you make a plant grow, you need to water a plant. This is how I remember it, at least. And you need to water it with liquid water, not steam. That makes sense? So, then for hydrocarbon combustion, you need to make the products of that. Basically, every combustion reaction, you need to add oxygen to make CO2 and water. So, oddly enough, it's actually, again, carbon dioxide and water, except this time when you blow something up, it's a gas. So 3, 4, and 3, 5. They would have accepted, by the way, like 4, 3, and 5, 3. Like that would have also been valid if you flip those around. So, does that work? Okay, this is also a very typical kind of question where I kind of mocked this earlier in the course. I don't know what teacher doesn't prepare their students for the question, where is the source of all of Earth's energy? It all comes from the sun. Okay, now this one's a little more tricky than that. It's not multiple choice, but we got to kind of put this in order. So, I mean, energy from the sun kind of comes first. Then what? Yeah, then that energy gets used in photosynthesis, causing plants to grow and animals to grow. And eventually those animals die out, or those plants die out, which is going to cause them to decay. And eventually then we'll dig them out of the ground as a form of oil and blow it up in our cars. Does that make sense? So that's a very standard question. This way that they phrased it here is maybe a little bit more tricky, but they almost always throw on one gimme question, which is basically, do you know energy comes from the sun?
Tony Fleur, please come to the office. Tony Fleur, please come to the office.
One of the things that you're going to find frustrating, that I find frustrating as a teacher to help you prepare for, I can probably... Oh my goodness.
Roger, please dial 103. Sylvan.
I can probably guess. I'm going to say 40 questions off your diploma, and I'll be able to tell you, expect this, expect this. But they actually even write this into the curriculum. They say that in order to get high marks, the 80s and above, they say that students need to be able to answer new and unique questions that you've never seen before. And I find that frustrating because how do I teach students to answer questions that are based on stuff that I have no idea what it's going to be on? Does that make sense? And that's what they're going to put on the diploma. And this might be a good example of one of those, where this is not an outcome of anything that we've actually really talked about. So, like there's no Q equals MC delta T here. This is kind of, you got to be able to interpret and problem solve. You guys had a chance to at least read this over? So if they give you a chart, methane, ethane, butane, and octane, and then they basically ask you to make an interpretation, one of these 4 answers is possibly true. Okay, well, as I look at the list, it looks like it's going from the smallest to the biggest numbers. Okay, now they're negative. What does that mean? Good. The bigger the negative number, the more energy released. So in my interpretation of looking at this chart is that octane gives off a lot of energy. It's very explosive. And methane, although explosive, doesn't give off as much energy per mole. Does that make sense? So that's what this chart is meaning for you to imply. Okay. It wouldn't hurt, though, to know what these chemicals are. So there's a table in your data book that should have most of them listed. By now, I'm expecting you guys probably know what methane is. Anybody know what ethane is? I hear Baxter's voice. Okay, anybody know what ethane is?
C.
Sorry, that's methane. Ethane.
C2H6.
Okay, anybody find butane?
C4H6.
Okay, Brad's on this. Does everybody know where to find this information, by the way? Okay, you're just not doing it because he's on it. Okay, Brad, what's octane?
C8H18.
Okay. I'm not even going to look at the 4 answers. What do you notice about these molecules as they get bigger? Sorry, I guess I just gave it away. There's more carbons. They're getting bigger. Does that make sense? Which maybe is logical. As molecules get bigger, so does the energy given off. So let's read through them. An interpretation is that the greater the number of carbon atoms, okay, so as we go down, is there lower energy stored in the molecule? I think that seems false because it seems like there's more energy. The greater the strength of the covalent bond? Well, I'm not really sure we can answer that question. Covalent bonds, it's been a while since some of you have talked about this, but covalent bonds are the bonds internal, and they're the ones who are supposed to share the electrons. That might be true, but I feel like this is probably the better answer here. The greater the energy released during combustion, because as we get bigger molecules, there seems to be more energy releasing during combustion because, hey look, it says it talks about combustion. Does that make sense? This is a tricky question for a lot of kids because I will never have specifically taught you something like that. You'll have to be able to make your own inferences. Does that make sense? Okay, let's do one more here. I'll give you guys a second. This one's a math one, so give this one a try. Hopefully as you look at it, you kind of recognize right off the bat what kind of question it's asking you about. It's another one of those Q equals MC delta T questions, right? You probably picked that out because they give you a temperature change, so. So you probably start with Q equals MC delta T. Why am I not doing the delta HN kind of stuff here? Yeah, I mean, it already gives me purely how much energy there is. So this number right here is 5.93 kilojoules. This is 120 grams. We don't know what C is. Well, we know what C should be. What should the C value be? So hopefully when we're done, it is 4.19, but we don't actually know that. And then the change in temperature, what is that, 11.5 degrees? Yeah, 11.5. Okay, this isn't gonna work if I do it like this. Anybody know why there's a mistake written the way I have it right here?
Because it has to be in joules, not kilojoules.
Good job. Yeah. One of the things they may try to do to mess with you is the C value. Standard C value is in joules as opposed to kilojoules, but so many other times we actually make things in kilojoules. So you may want to convert this number to 5930 joules. Times it by 1,000 and put it into joules just to make it easier. So I would solve for the C value first. So 5930 divided by 11.5 divided by 120. So I calculated the C value to be 4.297. You able to get to that? Is that right? Is that my answer? That's not what it's asking me for. It's asking me for the percent difference. So this is another reason why I make sure to do a lot of labs. You guys need to know the percent yield and percent difference formulas. So maybe we should revisit those real quick. A percent yield would be what it actually is supposed to be, like what you get in a lab, divided by what in theory it should be. So like actual divided by theoretical times by 100. That's a percent yield. A percent yield should ideally be close to 100%. Sometimes it's over 100%, which is odd, but that's fine. That makes sense? A percent difference then is how far off you are. And so the best way of doing that is the formula actual minus theoretical divided by theoretical times by 100. So what did you actually get in this lab? You got 4.297 ... Theoretically, though, it's supposed to be 419. Also, theoretically, it's supposed to be 419 times 100. Looks like you're off by 2.56%. That makes sense? It's actually not bad for a lab. I mean, in a high school lab, my general rule of thumb is if you're within 10%, that's pretty solid. If you're closer than, like, say, 5%, that's really good. So, and there's some labs where you won't even be all that close, like our first lab this year. Anybody actually do the math for yesterday's lab and kind of figure out how close they were to the accepted values? You were supposed to get, I think, 57 kilojoules per mole. So, I mean, if you're, I don't know, in the 50s or 60s, that's pretty good. I mean, if you're in the 40s or 80s, that's not bad, I guess. But okay, questions? Can you guys do this? Those are old diploma questions, by the way. Like, those are straight off of old tests. So that's kind of the expectation. So I feel like I can tell you expect certain things. The one that's going to frustrate you is the twists they throw at you, where it's, well, like that question before this one. You need to be able to interpret what information they give you and figure out how to apply it to solve the question. Because, I mean, I guess now you know, okay, the bigger the molecule, the more energy it should have for combustion. But if I don't teach you that beforehand, then how would I know then? Sound good? Okay. You guys still good to keep going and we'll take a break partway through? This is kind of an awkward time. It's going to be a while still. Okay, let's talk Hess's Law. Let's fast forward here. Okay, here is Hess's Law. It's a lot of jargon notation, and so I do want to make sure I try to teach you some of the symbols for this, but I feel like maybe it'd be better if I kind of ignore this slide for a little while, try to put this in people words, and then come back to what this notation means, if that's okay. So, okay, in our labs that we've been doing so far, both of the labs, I've asked you guys to try to calculate a delta H for some reaction. In the first lab, we would have loved to have found a molar enthalpy, but we couldn't do it for cereal because we don't know cereal's molar mass. So we did it per gram. But most of the time, this is what we're trying to find. Does that make sense? That was our goal in both labs. Try to find this number. And this number basically would be something like negative 57 kilojoules per mole. It lets you know how much energy is either released or absorbed per amount of substance used in a reaction. Does that work so far? The main way of trying to find this then, to like know these values, to do exactly what we do in the lab, you do calorimetry. You find an MC delta T, so you do a whole mass times this times delta T, and you divide by a number of moles, and that will find you what you're looking for. Here's the problem. There are certain reactions which we really can't safely do in a lab setting and actually do calorimetry data on it. For example, let's say that in the course of doing some reaction, it releases a poisonous gas. That's not exactly safe to use in a calorimeter. Does that make sense? We're actually going to do one on Thursday where we're going to burn magnesium. Have you guys ever seen magnesium burn? It's very hot. It's very bright. You really shouldn't stare at it for too long because it's going to hurt your eyes. And you'll see right away when I demo the reaction, I do it under the fume hood. There's no reasonable way we can put that inside a calorimeter. Like it's not smart. The other problem is maybe there are certain reactions where most of the energy is supposed to be heat. But what if some of the energy released is in the form of light or sound or some other form? Okay? So there's going to be occasions where hopefully you'd agree with me where doing a calorimetry type test is just impractical, it's unsafe, it's not going to be very efficient. Does that make sense? So Hess's law was discovered, and it's a roundabout way of getting there. And maybe the best way of me showing you how to do this is actually through a math example. I've taught all of you math. Good. Do you guys remember what a system of equations is? This is a good starting point. You're not actually going to do a system of equations, by the way, but it's a good starting point. Let's just review the concept. If I give you x plus y equals 7 and x minus 2y equals 5, I've shown all of you the concept of how you could stack these two equations and maybe you could subtract them. So then you'd say, well, x minus x goes away, and y minus 2y would give you 3y, and 7 minus 5 would give you 2. Divide by 3, y is going to be 2/3. Is that a concept that you kind of recognize? That works? Okay. Well, chemistry is similar. We can do similar concepts in chemistry, only we're going to stack equations. But when we look to eliminate things, in chemistry, we don't eliminate things top and bottom. That's not how it's going to work. Let me show you a different example. Let's say that, I'm just going to use letters again. Let's say that element A plus element B turns into element C and element D. And I want to stack that reaction as element C plus element F turns into element A plus element M. And I wanted to stack these reactions. Here's how I would eliminate instead. C was a product right here, and here it's a reactant. Those would cancel. That makes sense? Because what's going to happen is stuff is going to turn into C, but then later C is going to get used up again. What other thing would cancel in this example? A, yeah. Because here you start with A, and A gets used up, but later A gets produced again. So what we could do is we could combine these reactions and say that the net reaction is now B plus F turns into D plus M. Do you guys see how that's similar to a math system of equations? But rather than stacking them and trying to cancel things on top of each other like these X's are right here, what we're going to look for is try to obtain a product on one side and a reactant on the other side, and we'll try to, again, it's like elimination, we're going to cancel. Okay. Here's the other thing though. Let's say that I told you that this reaction right here took, let's say this was 100 kilojoules per mole. And this reaction right here was 200 kilojoules per mole. Anyone want to hazard a guess as to what the new combined reactions enthalpy would be? If this one's 100 and this one's 200? 300, yeah. Wouldn't that kind of just make logical and intuitive sense? Okay. That's what Hess's law is. Okay. So what we're going to do today is, rather than trying to find a delta H for a reaction by doing it through a calorimeter, what we're going to do is we're going to take multiple reactions and we're going to add them together as though they're a system of equations, and that will help us find the delta H of an equation that is maybe unsafe or impractical to do. That makes sense to start? So let me go back up to the slide here and then try to put this into people words, because this is jargon. Okay, so Hess's law. Okay, if you add some chemical reactions, so just like how I stacked them on top of each other and canceled things out, the net chemical equation means that the enthalpy change is really the sum. So add up all of the individual enthalpy changes. What I mean by that is, if this guy right here is 100 kilojoules and this one down here is 200 kilojoules, this bottom reaction, this would be the net reaction, it would be 300 kilojoules. That's all. So it's really an exercise in like a math puzzle. In terms of other jargon, delta H, delta refers to like a change in enthalpy. A change in enthalpy for a reaction is the same thing as adding up like a first reaction, a second reaction, a third reaction. However many reactions have to occur to make this work, if you add them all together, that is another way of getting the enthalpy you want. Okay. The last thing I want to show you is this symbol, in case you ever see this in some other place. Has anyone actually ever seen that symbol before? No idea what it means though? Okay, this is a Greek letter. It's called sigma. Okay. And sigma refers to, basically it means like the sum of, is kind of what it refers to. So if you ever see this sigma notation right here, it means add up a whole bunch of stuff. So like looking at the line above here, what this really means is add up the first reaction and the second reaction and the third reaction. Basically just add up all the reactions until you have no more reactions to add. What am I doing so far? Does that make sense? Okay, let's try some examples. I'm going to come back to the analogy in a second here. Can you guys find this example way further in the notes? Let's just try an example first, and then I'll come back to the stuff I skipped. Yeah, you need me in the hall? Okay, sorry. Read this over and then we'll talk.
Hey, you're gonna come and chill with us, dude. I don't even know if I work. Wait, you're gonna come chill with us, dude. Oh yeah, what's that?
Okay.
You're playing on that slide?
Oh my goodness. Okay, I'm sorry. How did this not end up in the notes? Okay, do you have this slide here?
Yeah.
Okay. And you don't have this slide. That is so silly. Okay, can you guys, underneath this information right here, can you guys write these two equations down right here? Sorry, this is going to take a little longer than I was expecting. How have I never picked up on this? Okay, so here's what the scenario happens to be. On the slide that you guys actually have, there's a reaction where they're trying to create carbon monoxide. Okay, is creating carbon monoxide a smart idea in a lab? Why? Yeah, it's poisonous. That's probably not a good thing. Sorry, anybody want breakfast? So this would be a good example as to why Hess's law would be useful. Doing calorimetry with Hess's law, like imagine that we were doing our first lab where we're burning stuff, and I was an irresponsible teacher, and one of the byproducts was carbon monoxide. That'd be really bad, right? So what we might do instead is we might find some data on other reactions which are more safe. One of the reactions right here involves creating carbon dioxide. By the way, does anybody want something? Thanks, guys.
Okay, everyone wants to starve today.
Apparently. So the first reaction involves making carbon dioxide. is carbon dioxide safer? I mean, maybe not environmentally as friendly, but safer. The second reaction, although involving carbon monoxide, is better as well because it's taking carbon monoxide and removing it and turning it into carbon dioxide. Okay. What our goal now is we're going to try to set up a system of equations, only it's like a chemistry version of it, and we're going to try to take these two reactions for which we have data, and we're going to try to manipulate it to make the equation of this equation right here, try to produce this one. So this equation is a carbon solid plus 1/2 of oxygen is going to turn into carbon monoxide. So maybe for the first one, I should just describe to you how I go about solving this. We want to try to produce carbon monoxide. Do any of these reactions right here have carbon monoxide in them? Which one? Okay, here's the problem though. This reaction right here has carbon monoxide as a reactant. We need it as a product. Now in math, if I go back to just a math example, if I told you that x plus 2y equals 7, is it not fair to also say that 7 equals x plus 2y? Can we not flip it backwards? Okay, well in chemistry, that works as well. If I told you that A turned into B plus C, I can flip the reaction and say that B plus C turns into A, but there's one side effect. If this reaction right here was, say, endothermic, the flipping reaction should probably be exothermic. Does that make sense? So what I'm going to do here is I'm going to say this bottom reaction right here, it has carbon monoxide. I can use carbon monoxide, but I don't want it as a reactant. I want it as a product. So I'm going to flip this reaction backwards, and I'm going to write it like this. This 2 CO2 is going to go here. It's going to turn into oxygen and 2 carbon monoxide. But then this delta H right here, which was negative 566, I now have to make it positive 566 kilojoules. Does that make sense so far? Okay, I have another problem though. I am aiming to try to have 1 carbon monoxide. And this reaction right here currently would give me 2 carbon monoxides. So again, can you cut a reaction in half? Sure, I don't see a problem with that. But where would that end up changing? Like this, you could make that 1. This, you could make this a half. This, you could make that 1. The energy value should also get cut in half. So then 566 would get cut in half to give you 283. At this point here, I've now managed to make carbon monoxide show up on the side I'm looking for. Now I'm going to pick another reactant or product that I want to try to aim for. I need some carbon over here. Do any of the reactions above have carbon in them? The top one does. Do I need to flip it around to get carbon in the right location? Okay. Do I need to cut it in half or double it to get it in the right location? I'd say no. So if I just write the first equation as is and say 1 carbon plus an oxygen turns into a carbon dioxide, then I don't need to cut this number in half. I don't need to flip this number around. I'm just going to write it over here as negative 393.5 kilojoules. Okay. Now is the time for me to kind of check my work with the system of equations concept and see whether I can get stuff to either cancel or to try to fit. Okay. Right here I have 1 carbon. There I have 1 carbon. That's good. Right here I have 1 carbon dioxide. Right here I have 1 carbon dioxide. Sorry, those are monoxides. Right here I have 1 carbon dioxide. But do you see how over here I have a carbon dioxide? And they're on opposite sides of the equation? Those cancel. On the reactant side over here I have an oxygen. But then on the product side I have half an oxygen. So I guess half of it cancels. So is it logical that you still have half an oxygen left here? I agree. So here's what we've now done. We found a way to take an unsafe reaction. This one down here, a little bit unsafe to do in the lab. But I took 2 other reactions which were a little bit more safe to do, and I'm going to piece them together. And so all I have to do now, according to Hess's law, is add this number and this number. So I'm going to take 283 as a positive, and I'm going to, I guess, subtract 393.5. And I get a new delta H now of negative 110.5. Does that make sense? So to answer the original question back here, the question here is, what is the enthalpy change? Well, the answer is negative 110.5 kilojoules. And I can actually make it per mole because there is 1 mole of carbon dioxide showing up right there. And so it's a roundabout way of getting to the answer. I skipped an analogy on one of my first slides here of a bricklayer. I don't know if this kind of helps you understand why we're doing what we're doing. Ideally, we'd like to go from here to here. But hypothetically, for some reason, doing some experiment, going directly from here to here is unsafe. It's impractical. It's just, for whatever reason, we just can't do this reaction from here to here. But we'd like to know what its enthalpy change would be. Well, what we could do is do reaction 1, reaction 2, and hey, look, we're in the same spot. Does that make sense? You do it in pieces, and you kind of like manipulate and fit them together like a puzzle. How am I doing so far? Does that make sense? Let's try another example. Okay, so here's some of the things we did. If you reverse a chemical reaction to make it fit, change the sign. And if you have to change a coefficient, then do the same thing, double or triple a reaction. Let's find another example to do here. Do you guys have this one on us? Okay, so let's give this one a try. The question is, let's try to find the standard molar enthalpy of formation of butane. So, what is butane? C4H10. C4H10. Okay, so for some reason, let's say that it's just not safe, not practical. For some reason, you can't do this yourself. But what you can do is take some data that you found elsewise and find a way to piece this together. So the first question I have is, well, what would the formation of butane look like? Well, formation of butane would involve you having to form the C4H10. When you form something, what do you form it from? Do you guys remember? You form it from its elements. So carbon comes in groups of 1, and hydrogen comes in groups of 2. And to balance it, I'm going to need 4 carbons and 5 hydrogens. So this is the reaction that we're hoping to do, but indirectly. We're now going to take all of these formulas up here and find a way to piece them together to make this bottom one. So if you like puzzles, you'll like this, because that's really what this is. This is like a puzzle. So here's my recommendations. I try to start with something like C4H10, and I'm going to look for C4H10 in one of these top reactions. Is there a C4H10 in one of them? Top one, right? Is it on the right side, though? Okay, so what I'm going to do is I'm going to take that top reaction, and I'm going to reverse it. And that's fine, as long as I take this number right here, and I also reverse it. So I'm just going to write this out below here. We're going to want 4 carbon dioxides, 5 waters. It's going to turn to 13 over 2 oxygens and the C4H10 I need. And the number is now positive 2657.4. And then I usually like underline just to say, okay, I've got that one in the spot I need. So far, so good. Pick another element that we need to try to put in the right location. Yeah, let's do the carbon we need right here. Do any of these reactions up here involve carbon? The second one does. Do I need to flip the reaction? Okay, but there is another problem though. See how this reaction right here has 4 carbons? And this one only has 1. So I can fix that. I will just make this reaction 4 times bigger as long as I take this number right here and also make it 4 times bigger. So I'll write out 4 carbons plus 4 oxygens makes 4 carbon dioxides. And I need to take minus 393.5 and times by 4. So I've got negative 1574 sitting over here. And then I might underline the carbon and say, hey, that's in the right spot. Okay, so we found the butane in the right location. We found the carbon in the right location. I just need to get some hydrogens. So, does one of these equations involve hydrogens? Yes, it does. The third equation. Is the hydrogens on the right side of the equation? Technically, it's actually on the left side of the equation, but it's on the correct side of the equation. Sorry, that was bad. There's 2 here. You need 5 there. How do I fix that? How do you turn 2 into 5? Yeah, times by 2.5. Okay, you can times by partial numbers, by the way. That's valid. So if you times this by 2.5, this will now be 5. That'll be 2.5. That'll be 5, and that'll be times by 2.5. So we need 5 hydrogens, 2.5 oxygens, 5 waters, and if you take 483.6 and times by 2.5, you get, I got 1209. Anybody else get that? Does that make sense? At this point now I would say, look, here's my hydrogens. There we go. If this is done correctly, everything else should, kind of like a system of equations, should just magically kind of cancel and fall into place. So, look, here's 4 carbon dioxides. Does it have something to cancel with? Yeah, look, over here there's 4 more carbon dioxides, 1 on each side. So that one and that one should cancel. Here's 5 waters. But lo and behold, look down there, there's 5 waters. This should cancel. 13 over 2 is 6.5. Here's 4 oxygens. Here's 2.5 more. That's 6.5. 6.5 over here, 6.5 over here means these guys all cancel. What I am now left with is 4 carbons, 5 hydrogens, so 4 carbons, 5 hydrogens, makes my butane. So to find the delta H number for this reaction right here, all I have to do is take this number, and this number, and add them up. So 1257.4 minus 1574, also minus 1209. So this number right here, I got negative 125.6. The units would be kilojoules because all of these numbers were in kilojoules. Okay. Now, that's not quite done though. This question actually wanted the molar enthalpy. So we need to know per mole. But here's the good news. How many moles of butane is showing up right here? 1. So since there's only 1 sitting there, you could say that your answer is that many per 1 mole. And there's our answer. So one more time. Why would you do this? Well, honestly, you would only do this if you really had to. If it was unsafe, impractical, you didn't have the materials. Okay. On Thursday, we're going to do a lab, like I said, where we're going to try to find out how much energy you get from combusting, from burning magnesium. But I can't safely hand you guys some magnesium and say, put this underneath a tin can. It burns too bright, too quickly. Most of the energy is in the form of light. That makes sense? It's impractical. But what I can do is show you how to do 3 other reactions, which we can solve, and then by jury rigging and like rearranging and piecing it together, we can get the answer we're looking for. Does this make sense? You guys feel comfortable? It is. It sucks, by the way. You're going to get one of these for sure in the diploma, and you need to budget like 5 minutes to solve it, because this takes longer than the average question. So you have to make sure that you can do some other questions in a little bit less time, because this one just, it takes a while. Why don't you guys take a break, and then we'll finish up whatever details I haven't gotten to yet. But that's more or less the gist of what you need to know. Okay, okay so far? Okay, so let me just do one last example with you. Maybe put a big star slash something in your notes to look back at this particular one, because this, 1 year on the diploma, they put on a Hess's Law question. That was really, really mean. Normally what they do is they give you some equation, they just ask you find the delta H, and you just do what we just did there where you try to piece them together. 1 year, they made it numeric response. And in making it numeric response, they listed a whole ton of different equations. And they asked, in order to produce this equation, which of the following equations
Shelby Stelbastine, please come to the office.
And
Shelby, please come to the office.
there was more than one right answer. Which, like, that intimidated kids. Because, I mean, you'd normally think, well, if there's more than one right answer, then that makes it better. But sometimes it makes them more confusing. And so I wanted to show you this example here. This came out of your textbook. Our goal is to try to produce this reaction right here. And I'm not actually going to calculate the number. I'll assume you guys can handle that part later. I just want to see whether we can try to find different ways that we can organize some of these examples here from 1 to 8 and figure out which ones possibly could get us to this example. Does that make sense? So we'll try to find some combos that work. So, okay, so for the first one, the way I was looking at this is we need to obtain a carbon monoxide. And as I look up on these ones here, lo and behold, the very first one involves carbon monoxide. So I could use this first reaction. I would have to cut it in half, but that's okay. So I might say we could use reaction 1, and we'll use 1 carbon, we'll use half an oxygen, and it'll make us 1 carbon monoxide. So that covers this guy right here. We also need to have some methane. Any reactions below here involve methane? 2 and 5 both involve methane, don't they? I could go with 2. As I look at it, I think I actually want to try to use 5 though. The reason why I think 5 might be clever to use, you see how CH4 is on the wrong side? I would have to flip it around, which is fine. I can do that. So if I flip around CH4, throw it on this side, it means it would turn into carbon plus 2 hydrogen, and I'd use 5. But do you see how this carbon and that carbon would cancel? It's kind of clever. We also need some water. Any reactions involving water? Well, actually, like a ton of them involve water. But this one right here is kind of unique. It involves water, which we need. It involves oxygen, which right here we need to get rid of. And it involves hydrogen, which we also need. That'll work. Okay, so let's cut it in half and flip the reaction. So if I cut this one in half and flip it, you'd have water on this side. You'd have half an oxygen over here, and you'd have I made a mistake. There's supposed to be 2 hydrogens there. And you'd have 1 hydrogen right here. Okay, so take reaction 1, cut it in half. Take reaction 5. What did we do to 5? We flipped 5, right? Take reaction 4, flip it, cut it in half. Now water is sitting where we want it to be. Hopefully you can see that this half oxygen cancels that half oxygen. There's the carbon monoxide where we need it. There's the methane where we need it. And these hydrogens right here add up to be the 3 we're looking for. So the way that they phrase this particular diploma question is the answer would have been 1, 4, and 5. I don't think they care which order it was in, but those are the equations that would have worked. If you use 1, 4, and 5, it would get it to work. Does that make sense? Okay, let's try to find another way. You know how my initial premise was that I needed to find some carbon monoxide? And this one right here has carbon monoxide. This one down here, number 6, this one has carbon monoxide. So maybe I'll start with question number 6 and see what I can do with it. Carbon solid. and water vapor would give you carbon monoxide and hydrogen. So my carbon monoxide is where I need it to be. And good news, actually my water vapor is also where I need it to be. So things are looking good. I need to find some reactions then that involve methane.
5 again.
5's not a bad idea, isn't it? Let's take methane reaction, the one above there, and let's flip it backwards though, right? So if we take 5, but we flip 5 around, it would mean that you take the methane, throw it over here. You would throw the 2 hydrogens on this side and a carbon on this side. This actually works out perfectly. That carbon cancels with that carbon. That's the methane where you want it. And look, 1 plus 2 gives you 3. So another valid answer would have been 5 and 6. Does this make sense? This was intimidating. I feel like a lot of kids, when they saw this question on the diploma, they freaked out. Because they were so used to doing a Hess's Law question where the question asks you, find me the value, and they give you 3 equations, and you just use the 3 equations, and you flip them around, and there's your answer. And this one was too open-ended because they give you like 9 or 8 different questions, and they say, you don't have to use them all, but find a way of solving it. So I want you guys to be aware of this one here. I don't have a lot of examples I can show you like it, because I've only seen it on one diploma, but I want you ready for it in case it does show up. So, does that make sense? Okay. So summary of the day, Hess's Law is very not purposeful, honestly. I mean, this is the longest way of trying to solve a question I could think of. It's very roundabout. You would need to have a whole bunch of reactions that you know information for. You have to kind of piece them together like a puzzle and try to find the reaction that you are looking for. So reasons why you would be doing this: it's impractical, it's ineffective, it's unsafe to perform a certain reaction. So you do the roundabout method, where, like if you like the stairs analogy, rather than going directly up the stairs, you go like up 1 set, up 2nd step, and they get you to the same spot. The notation you might see then looks like this. You might see that little sigma notation. It's like a fancy looking E, and it basically means add up all the steps. Any questions? Okay, there's about half hour left today. Here's my suggestion. You're gonna want to practice this a few times. Like, you don't need to practice it, for forever, but I do have a worksheet on my website, which has got some Hess's Law practice questions. It wouldn't be a bad idea to try a couple of those just to practice, but once you get the concept, they're all the same. Like, it's the same thing over and over again. You can also probably answer another one of the questions on your assignment now. One of them very specifically involves Hess's Law, and you'll see them because they'll be very unique, because they'll give you a little preamble, and they'll give you like 3 or 4 different equations, and they'll ask you to solve for another equation past that one. So, other than that, work on your lab. Can I have the serial labs due for tomorrow? And I'll try to finish them off before the end of the week so you can know how you did. And then the lab we did yesterday, we'll have that be due the Monday you guys come back from your week off. Does that work? Right. Cool. Let me know how I can help with stuff then.